This is another method that is high pressure method for the synthesis of inorganic materials, hydrothermal methods. The original hydrothermal method involved heating the reactants in a closed vessel, and this closed vessel is called autoclave, and autoclaves have water in it. Uh, an autoclave is usually constructed from thin stainless steel. This is a strong material and it can withstand a high pressure because high pressure is generated inside the autoclave, and the stainless steel is a strong material and it can withstand high pressure. And it is fitted with safety valves because the high pressure is involved, so safety valves are also present. It may be lined with non-reactive materials such as Teflon. So autoclave, in the autoclave, the material which we are putting in the autoclave can react with the stainless steel at high temperature. So Teflon is coated inside the inside of the autoclave, and Teflon is unreactive material. It will not react with the reactants at even at high pressure and high temperature. The autoclave is heated. The pressure increases. When the autoclave is heated inside the autoclave, the pressure is increases when the autoclave is running. Water remains liquid above its normal boiling temperature because the external pressure in the autoclave is high above the surface of water. So when external pressure is high, the boiling point of water will increase. And at 373 Kelvin, water will not be converted to gaseous form. It will be in liquid form due to high external pressure. So called superheated water, so the temperature of water will be high. It is called superheated water. These conditions in which the pressure is raised above atmospheric pressure and the temperature is raised above boiling temperature of water. These conditions are maintained here. That is, the pressure inside the autoclave is greater than the normal atmospheric pressure, and due to this high pressure, the boiling temperature of the water increases as compared to 100 degrees centigrade. The term has been extended to other systems with moderately raised pressure and temperature lower than those typically used in ceramic and sol gel synthesis. Um, this term, that is hydrothermal method. Hydrothermal method term is also used for other synthesis method, for other system, like where there is moderative increase of pressure and temperature are lower than as compared to ceramic method and sol gel method. So all these methods in which the pressure is high as compared to ceramic and sol gel method and temperature is low, all these methods will be included in the hydrothermal method. So this is the autoclave, which is used commonly used in hydrothermal method. The lower temperature used are one of the advantage of this method because the less energy will be required and there are less chances of decomposition of the product. Others include the preparation of compounds in unusual oxidation state or phases in which are stabilized by the raised temperature and pressure. Mm. Its other advantages are, by the hydrothermal method, we can prepare the compounds in unusual oxidation states. Mean the oxidation states which are not common, which are less common, we can prepare the compound with these oxidation states by hydrothermal method. And the hydrothermal method can be used for preparing the phases, which are phases of the compound which are stabilized by high temperature and high pressure. It is useful in metal oxide system where the oxides are not soluble in water at atmospheric pressure but dissolve in the superheated water of the hydrothermal setup. So this method is very useful for metal oxide synthesis, and metal oxide are the compounds which are not soluble in water at room temperature but they will be soluble in that superheated water which is present in hydrothermal setup. Now we will study the synthesis of quartz. Quartz is silicon dioxide, crystalline form of silicon dioxide, and it can be synthesized by hydrothermal method. Here in the diagram it is shown. In the first industrial process to use hydrothermal method of synthesis was the production of quartz crystal for use as oscillator in radios. So quartz crystals was manufactured for radios. They are used as oscillators in radios. Quartz silicon dioxide can be used to generate a high frequency alternating current via the piezoelectric effect. Quartz silicon dioxide is a piezoelectric material, and so it will produce a high frequency alternating current through piezoelectric effect. We have already studied the piezoelectric materials. The hydrothermal growth of quartz crystals employ a temperature gradient. When in the hydrothermal method, the crystals of the quartz are growing. Due to this growth of the crystal, some parts of the uh, solution will be hot and some parts of the solution will be cold. The temperature gradient will be formed, temperature difference will be established. In this variance, that mean the temperature gradient or temperature difference which is established in hydrothermal process, the reactant dissolve at high temperature. At the high temperature, the reactants which are used for the synthesis of silicon dioxide will be dissolved at high temperature, and it is transported up the reaction tube by convection and crystallizes out at a low temperature. So where is the low temperature, the crystals will be formed, that is at the above level of the tube there will be low temperature and crystals will be formed at low temperature. One end of the autoclave is charged with silica and alkaline solution. These are the reactants. Quartz is prepared from ordinary silica and alkaline solution. These are the reactants. So one end of the autoclave is charged with these type of reactants. When the autoclave is heated, the silica is dissolved in the solution and is transported along the autoclave to the cooler part where it crystallizes out. So the crystals which are formed of the silica will be of quartz crystal. Quartz is also silica, but it is a different crystalline form as compared to ordinary silica. The alkaline solution returns to the hotter region where it can dissolve more silica. So the alkaline solution returns back towards the hot region, and here the silica is present in the hot region and it will dissolve more silica, and then it will move to colder region and where the crystals of quartz will be deposited. In this particular case, the autoclave which is made of steel can act as a reaction vessel. So the autoclave made up of steel, this autoclave as a whole react as reaction vessel. We can put directly the silica and alkaline solution in this stainless steel vessel. High pressure gases. This method is usually used to prepare metal oxides and fluorides. Previously, we have studied hydrothermal method, which was the first method we have studied in high pressure method, and this is the second high pressure method, that is high pressure gases. And it is used to prepare metal oxides, fluorides in less stable high oxidation states, the states which are less stable and high oxidation state. For instance, the perovskites, that is strontium iron oxide containing iron 4, because iron normally exists in iron 2 and iron 3 form. This iron 4 form is a very unstable oxidation state of the iron. So for preparing this unstable oxidation state of iron, we can use this high pressure gases method. This synthesis, perovskite strontium iron oxide synthesis, can be made from the reaction of strontium distrontium diiodine pentoxide and oxygen at the 340 atmosphere. A high pressure is applied, and what are the reactants? Distrontium diiodine pentoxide and gaseous oxygen. Using fluorine at high pressure, that is greater than 4 kilobar, has also been used in the synthesis of ternary fluorides. These are ternary fluorides. So in this case, in the above case, the high pressure of oxygen is used, and in the below case, What gas is used? Fluorine gas at high pressure is used for the preparation of ternary fluoride like this compound, cesium copper fluoride. Containing high oxidation state, for example, cesium copper fluoride, the copper normally exists in two oxidation states, but here is copper in +4 oxidation state, which is very rare, less common, unstable, and it can be prepared by using fluorine as at high pressure. Hydrostatic pressures. The application of high pressure and temperature can induce hydrostatic pressure is another high pressure method for the synthesis of inorganic material. The application of high pressure and temperature can induce reaction and phase changes that are not possible under ambient conditions. Ambient condition mean normal conditions. So, due to high pressure and high temperature, reaction rate can be speed up, and it can induce reaction, it can start reaction, and it can undergo that phase changes which cannot normally take place at normal temperature and normal pressure. Applying very high pressure tend to decrease volume and does improve the packing efficiency. Um, by increasing of pressure, the molecules come close to each other, and when they are close to each other, they are efficiently packed, and they are close to each other, they will collide to each other, and they will react to each other, and reaction speed will be more. Consequently, coordination number tend to increase. When the packing is more, the coordination number is increased. So, for instance, silicon can be transformed from 4-coordinate diamond structure to 6-coordinate white tin structure by using this hydrostatic pressure method. Means the pressure is applied by water. And sodium chloride, which is 6-coordinate, can be changed to cesium chloride 8-coordinate structure by using this hydrostatic pressure method. Originally, a piston and cylinder arrangement, that is normally a piston is used along with a cylinder for increasing the pressure. So this method can be used for increasing the pressure on the reactants, piston and cylinder. Arrangement allows synthesis at a pressure up to 500 gigapascal, that is 50,000 atmosphere and 1800 Kelvin temperature. This temperature and this high pressure can be achieved by normal piston and cylinder method. We will apply pressure through the piston and we will keep the reactants in the cylinder. But here is another method, that is belt apparatus. Belt apparatus using two opposed tungsten carbide cylinders, which is in opposite direction, can reach in this belt apparatus, which is having two opposed tungsten carbide cylinders. It can achieve even high pressure, that is 15 gigapascal, and temperature even high, that 2300 Kelvin, and it is used for making synthetic diamonds because diamond synthesis requires very high pressure. Another high pressure apparatus is diamond anvils. Here the diamond anvils, two diamonds are placed. This is one diamond, second diamond, and they are placed in opposite direction. In between the diamond, here on the tips of the two diamonds, the material is placed on which the high pressure is applied. From both sides of the diamonds, pressure is applied, and here the material experience very high pressure, and this type of cell is called diamond anvil cell. So diamond anvil has been used to reach pressure of 20 gigapascal. Very high pressure is maintained here on the tips of the diamond. Diamond anvils can be arranged either two directly opposed. These are two directly opposed diamonds. Four tetrahedrally opposed. Here we can use four diamonds. One diamond here, one diamond here, and six. We can use 6 diamonds in octahedral configuration, but although they achieve greater pressure than other methods, the pressure in diamond anvil cell is very high as compared to other methods. They have the disadvantage that 1 milligram quantities of material can be processed. Here on the tip, a very small quantity of material can be processed. So this cannot be used for, more useful for investigating phase transition than for synthesis. So for the synthesis, it is not suitable because a very small amount of material can be mounted here, but it can be used for studying the phase transition. That is, one type of crystalline phase changes into other type of crystalline phase at high temperature, and these type of studies can be performed in these type of diamond anvils or diamond anvil cells. Synthetic diamonds. How synthetic diamonds can be prepared by high pressure method, growing crystals up to 1 millimeter in length by dissolving graphite in a molten metal such as nickel, cobalt, or tantalum in prophyllite vessel and subjecting the graphite to pressure of 6 gigapascal and temperature 2300 Kelvin until diamond crystals form. So diamond is prepared from its another allotropic form, that is graphite at very high temperature and at very high pressure, 6 gigapascal, very high pressure, very high temperature. And the graphite is dissolved in which solvent? Molten metals such as nickel, cobalt, tantalum, and the vessel is made up of pyrophyllite. The molten metal acts as a catalyst, bringing down the working temperature and pressure. These molten metals which are used here, these also act as catalyst. And what is the function of catalyst? Catalyst speed up the reaction. It lowers the activation energy, so it will lower the bringing down the working temperature. It will lower the temperature which is required for the reaction, and it will also lower the pressure which is required for the reaction because these metals act as catalyst. By refining the process, gemstone quality stones were eventually made in 1970. And the diamond stone were successfully made in 1970, which were of gemstone quality, mean which were of very good quality. Chemical vapor deposition technique is another technique for the synthesis of inorganic materials. It is most more advanced technique as compared to the previous techniques. In CVD, the powders and microcrystalline compounds are prepared. Very fine powders are prepared, and the crystallized size is very small in the material for materials which are prepared in CVD process. Compounds are prepared from reactant in the vapor phase and can be deposited on the substrate. So the reactants here are taken as in the form of vapor or in the form of gaseous. And here is the substrate, and the reactants, when they react and they will form the product will be deposited on this substrate, and this product will be in the form of thin sheet, thin film, etc. And the product is deposited on a substrate such as thin sheet of metal or ceramics to form single crystal film for devices. So here the single crystal film, very thin film is formed whose thickness is equal to a single crystal size, and this thin film which is deposited on the substrate is used for the application in many devices. First, the volatile starting materials are heated to form the vapors. They are then mixed at a suitable temperature and transported to the substrate for deposition using a carrier gas. So what will be done? Volatile starting material. The starting material is converted into gas and it is injected into this container. Starting material is heated to form vapors. It is converted into form of gas. Then the reactants are mixed at a suitable temperature. Here the suitable temperature is maintained and reactants are mixed here and transported to the substrate for depositing using a carrier gas. Here is also a carrier gas is present. So the reactants will react here and they will deposit on this substrate in the presence of carrier gas. The gas is coming in and then gas is going out from the here, and along with the carrier gas here the reactants are also present in the form of gas. Finally, the solid product slices out. The solid is formed on the surface of the substrate. The whole vessel may be heated. We tend to deposit the product all over the wall of the vessel. So whole the vessel, whole the container is heated up, so the products will deposit on all the walls of the vessels and also on the substrate. More commonly, the energy to initiate the reaction is supplied to the substrate. So the energy is supplied to the substrate and substrate will initiate the reaction. Typical starting material are hydrides, halides, and organometallic compounds because these compounds tend to be volatile. The starting materials, the reactants which are used for the synthesis in CVD are hydrides, halides, and organometallics because these can be easily converted into gaseous form. They are volatile. If an organometallic precursor is used, the method is often referred to as metal organic CVD, MOCVD, if organic metallic is used as a starting material or as a precursor. The advantages of this method are that the reaction temperature are relatively low as compared to the ceramic method. The temperature is low, the stoichiometry is easily controlled, and the dopants can be incorporated. Doping can be easily done in this method. Here we will study the synthesis of the different semiconductor materials like silicon, gallium arsenide by what method? Chemical vapor deposition method, CVD. The CVD method has been widely used for the preparing of the semiconductors from group third to group fifth of periodic table, and for many semiconductors and silicon, which is used in many electronic devices, these semiconductors can be synthesized by CVD. Various reaction to prepare gallium arsenide. Gallium arsenide is also a semiconductor material. It involves chloride and hydrides. In the starting material, we can use gallium chlorides or arsenic chlorides or gallium hydrides or arsenic and hydride form in the starting material. For the CVD methods, these have been tried. For example, one of the reaction is that where arsenic chloride is reacted with gallium to form the gallium arsenide in CVD method. In the presence of hydrogen gas, the carrier gas will be hydrogen. And here is another synthesis, that is synthesis of silicon. And silicon is a semiconductor material and it is used in many electrical devices. It can be prepared by using this method means CVD method, chemical vapor deposition technique, from the reduction of silicon chloride. Silicon tetrachloride reacts with hydrogen. It is reduced by hydrogen. It is converted to silicon and hydrogen chloride, and this silicon is in the form of deposit on the substrate. Silicon chloride is converted into vapors and hydrogen carrier gas, and when it deposits on the substrate, it will be very thin silicon layers. Here is the synthesis of gallium arsenide. How gallium arsenide can be synthesized? The reactant used are arsenic trichloride and gallium plus hydrogen as a carrier gas. So gallium arsenide and HCl will be formed, and here is the apparatus. Gas inlet and gas outlet, the reactants are converted into gaseous form. Hydrogen is already a gas. So all the three reactants are added in this reaction chamber, and where the substrate provide the energy for the reaction, and the gallium arsenide will deposit on the this substrate, and hydrogen chloride is a gas, so it will come out from here. And this is the deposition of gallium arsenide layer. This is a electron microscopic picture of gallium arsenide layer on the substrate. Diamond films can also be formed by CVD method. Diamond has many useful properties as well as being the hardest substance known. It is also the best thermal conductivity. At room temperature, it is an electrical insulator and has the highest transparency in the IR region of the spectrum of any known substance. So diamond has many applications in the field of science. It has many useful properties. One property is a hardest substance, so it is used for cutting off other hard substances. It is used for cutting off glass. It is also the best thermal conductivity. It is a good conductor of heat at room temperature. So this is also it's a good property. It is an electrical insulator. It cannot conduct electricity, and highest transparency in the IR region. It is transparent to IR radiation. So diamond films are made by CVD process at low pressure and temperature below 1300 Kelvin, at low pressure and temperature as compared to the previous methods. That is below 1300 Kelvin. It is prepared and it is heated by gas mixtures are heated, and the gases contain methane, which is a less expensive gas, or acetylene and hydrogen. These gases are heated in CVD chamber, and the diamond film will be formed on the substrate. And it can also be prepared by breaking down such mixture with microwaves. Uh, that is, these mixture containing methane, acetylene, and hydrogen, using microwaves. Uh, Breaking down such mixture by microwave by using microwaves, these synthesis can also be achieved. Carbon atoms and the carbon containing radical species are then deposited on a substrate. The carbon atom in the form of diamond will be deposited on the substrate. Early experiment managed to deposit monocrystalline layers onto a seed diamond and thus build up larger diamond layer by layer. So the experiment which was performed earlier, uh, in that experiment, the scientist was successful in depositing a monocrystalline layer of the diamond on a seed diamond. Seed diamond means the a diamond crystal which is used for initiating the reaction, for initiating the crystallization of diamond, for initiating the deposition of diamond layer. So seed diamond is used, and seed diamond monocrystalline layers were formed in the early experiment and thus build up larger diamond layer by layer. So more layer will be formed on that monocrystalline layer, and thus layer by layer diamonds were formed in the early experiment. Microcrystalline diamond layers have also been deposited on silicon and metal surfaces. Here in the above case is the diamond layer are deposited on a seed diamond. And in other experiment, diamond microcrystalline layers are also deposited on the silicon substrate, metal substrates. Such layers have been used for non-scratch optical coating, for coating knives and scalpels, so they retain their sharpness. Such layers, that is microcrystalline diamond layer. Because diamond layer is very hard layer, so what is the application of this very thin layer? It is used for non-scratch optical coatings. It is used on the optical materials. So optical materials, it will be diamond layer will be transparent, and it will be used for coating the optical materials. So optical materials will not undergo any scratching. That will be scratch resistant. For coating knives, so when diamond film is coated on the knives will be knives and scalpel, so they retain their sharpness. They will retain their sharpness for a long time, and have the potential to be used as a hard wear resistant coating for moving parts. This diamond coating can be done on the moving parts of the machinery. So moving part of the machinery will gain more strength. They will gain more hard wear resistance, because it is a diamond is the hardest material which is known. So there are many applications of diamond other than the most popular application that diamond is used in jewelry. There are a lot number of applications of diamond in science and in industries.